As we continue our discussion about rate laws, the next method in determining rate laws we're going to take a look at is a graphical method. So we had mentioned two ways. We had an initial rate method, we had a graphical method. So with graphical determination, as that name implies, we're going to be looking at graphs. Now, in your last exercise, you looked at using the initial rate method to determine a rate law and rate constants. Here we're going to look at our second method involving graphs. This involves examining graphical relationships between concentration and time. These relationships are derived through a calculus operation called integration. Now, we're not going to go into that because calculus is not required for this level of course. But we're bringing it up because these are derived equations. So we perform a calculus operation on them called integration, and we get from our rate law to what we call this integrated rate law. And so performing that calculus operation generates, again, what we call integrated rate laws. Each common order has its own integrated rate law as follows. So if we have a zero order reaction, so for zero order, and we're talking about right now just a single reactant, for that single reactant, the rate law for zero order would say that my rate equals K times the concentration of A raised to the 0 power. If we perform that integration on it, we're going to get the equation that the concentration of A at time t equals negative KT plus the initial concentration. For a first order, where rate equals K times the concentration of A to the power of 1, the corresponding integrated rate law would be the natural log of the concentration at time t equals negative KT plus the natural log of the concentration at time 0. And then finally, for our second order, so for second order, the rate law would be that my rate equals K times the concentration of A squared. So that integrated rate law would say that 1 over the concentration at time t equals KT plus 1 over the initial concentration. So in all of these equations, we're seeing A in brackets, so our reactant in brackets, and then we're seeing this T subscript. That is referring to the concentration at a particular point in time, corresponding to the point in time in our equation. We also see A, our reactant in brackets, with a 0 subscript. That is the initial concentration. Now, notice that each of these equations resembles the equation of a line. A line has a y equals mx plus b format. And if something has a y equals mx plus b format, that means we can graph information and we should be able to get a straight line. So if we have a zero order reaction, and again, that's if the reaction is zero order, and we were to graph concentration versus time, if that graph results in a straight line, the reaction is zero order. So we have an example here of concentration versus time, and we're getting a straight line. And notice here that our slope equals negative K. Now, if we were to graph that information, concentration versus time, and we did not see a straight line, that would indicate the reactant is not zero order. So we saw this earlier when we were looking at concentration versus time graphs to calculate things like initial rates or instantaneous rates. Those were curves. The fact that they were curves tells us our reaction is not zero order. Now, if we were to graph the natural log of our concentration versus time, if that resulting graph is a straight line, then our reaction is zero order. If the graph of the natural log of the concentration versus time does not produce a straight line, then the reaction is not first order. So again, we have an example here. We have the natural log of our concentration versus time. It's resulting in a straight line. And again, our slope is negative K. And then finally, if we were to graph 1 over concentration versus time, if that line is straight, the reaction is second order. If it's not straight, then it's not second order. So our example here, again, we've got 1 over concentration versus time. It's a straight line. Again, our slope is indicating K. So how we use this in terms of determining a rate law or to determine our orders. To determine our orders graphically, what we're going to do is we're going to make 3 graphs. We're always going to make 3 graphs. We're going to make a concentration versus time graph, natural log of concentration versus time, and 1 over concentration versus time. Then what we do is we compare those 3 graphs to determine the order. Not all of the graphs are going to be a straight line. The one that gives us the straight line tells us the order. So whichever graph is the most linear tells us our order. Now we want to draw all 3 because depending on our data, depending on how well we draw our graphs, some might look linear, but then we compare them and others may be more linear. So we'll take a look at an example of using this graphical method. So we've got a table of data that has time, concentration, natural log of concentration, and 1 over concentration. Now, if we're talking about rates, when we start any experiments, our experiments are going to start with concentration and time measurements. So again, we talked about that with determining rates, things like our instantaneous and initial rates and average rates. So we started with concentration versus time. So concentration and time are typically going to be measured. 1 over concentration and natural log of concentration, these are going to be manipulated. You're going to have to calculate those based on our concentration. Now, what we then see here, so again with the graphical method, we're going to draw 3 graphs. First graph we draw is concentration versus time. If we have a concentration versus time graph, that is a 0 order graph. If we look at the 0 order graph, we can see a distinct curve to it. The fact that that graph produces a curve rather than a straight line, that means that my order is not 0 order. Now down below this graph, we've got natural log of concentration versus time graphed. Now again, if you were drawing this, depending on your data and how you drew your lines, it may have appeared linear because it's definitely less sloped than that 0 order. But it's still got a slight curve to it. So it's natural log of concentration versus time. This is my first order graph. It again curves. Since it curves, that means my reaction is not first order. So then our final graph, we have 1 over the concentration of our reactant versus time. This one produces a straight line. This is our second order graph. Again, it's a straight line. That tells us that my order is second order. So when we're asked for the rate law here, my rate will be equal to K times the concentration of NO2 squared. That square is coming from the fact that the second order graph gives us the straight line. From our graphs, once we find which one has the straight line, all of our examples we looked at, we said that our slope was going to give us K. So K can always be determined from the slope of the straight line. So if we were to calculate slope here, and we've seen this already occurring on our graph here. So we're using these 2 points so we're going to have a value of about 340 for this point. My value at this point is about 150. So we're doing our change in y over our change in x, which is going to be about 400 minus 50, which is going to give me a k of 0.54. Seconds to the minus 1, molarity to the minus 1. So our graphical method, we take concentration and time information. We take the concentration information and we manipulate it. So we create a table, we create another column, natural log, go to our calculators, we take the natural log of all the concentrations. Another column, we do 1 divided by each of the concentrations. We then graph those. So we graph concentration versus time. Our second graph, which is a first order graph, we graph natural log of concentration versus time. And then our second order graph, which will be the last graph we draw, will be 1 over concentration versus time. Compare the 3 graphs. The one that gives us the most linear graph tells us the order. So in this case, second order graph was straight, so the order on my reactant was 2. From that slope, we can calculate our K. So we can use these integrated rate laws and the graphing of their variables in order to determine our orders, but we can also use them to get information about our reaction. And in particular, we can use them to get information about concentration and time. Now, before we get into that conversation, we want to talk about something called half-life. Half-life is very common to talk about when we discuss rates. We represent half-life with lowercase t, 1/2 subscript. It is the time it takes for the concentration to decrease by 1/2. It's determined from our integrated rate laws. There are derivations in your book if you want to take a look. So we're not going to go through those. But what that means is that it's going to be different for each integrated rate law. At the end of your worksheet, there is a table summarizing the different half-life equations corresponding to each order and each integrated rate law. For any order, the concentration left after 1 half-life is the initial concentration divided by 2. If we have multiple half-lives occurring, then our concentration after a certain period of time will be our initial concentration times 2 to the n, where n is the number of half-lives that occurred. So using these integrated rate laws in conjunction with our half-life equations, we can get information about our rate constants. We can get information about how our concentration might change over a given period of time. We can get information about how long it might take to get a particular concentration change. So here we have a chart. This is the chart at the end of your worksheet that summarizes our 3 common orders, their corresponding rate laws, their corresponding K units, integrated rate laws, and half-life expressions. This is a good resource to keep handy when you're working on problems out of this chapter, so you can refer back to those integrated rate laws and your half-life expressions. So we'll look at an example of using our integrated rate laws. So say we have a first order reaction for which the half-life is 1,140 seconds. And our reaction is the 2N2O5 producing 2N2O4 and oxygen. Now, the instant we're told something is first order, we know 3 pieces of information, which are going to correspond to parts A, B, and C of this problem. When we see that order, we automatically know 3 things. We know the rate law. First order is telling me that my rate equals K times the concentration of my reactant. It's first order, so remember we're going to leave that number off. It's understood that it's raised to the power of 1. So we're told first order. So we're told that order. If it's first order, we know our first order integrated rate law. So we know that the natural log of our concentration at time t equals negative kT plus the natural log of our initial concentration. We also know our half-life equation. So if we go to our chart, the first order half-life equation says that half-life equals 0.693 divided by K. So these are known all based on being told it's first order. We're now going to use a variation of these equations to solve for different information. So the first thing we're asked to determine is the rate constant. So I've got 3 equations. All 3 equations have the rate constant in them. So I need to consider what other information I have. And the only other information I have is the half-life. So I can use my half-life equation relating my half-life to my K. So we have 1,140 seconds equals 0.693 over K. We would rearrange our equation to solve for K. So K would be 0.693 divided by 1,140 seconds. So my K will be 6.08 times 10 to the negative 4th. Units, I have no units on top. I have seconds on bottom. So my units are seconds to the minus 1. So if I know half-life, I can use half-life to determine my equilibrium or my rate constant. At the same time, if I had known my rate constant, I could use that to determine my half-life. So looking at the next part of our problem, we're asked if the initial concentration of N2O5 is 6.94 times 10 to the negative second molar. We want to know how long it will take for the concentration to reach 5 times 10 to the negative 4th. So if we're looking, we want to know how long, we're looking for time. So again, I go back to my 3 equations from A, B, and C. 2 of them have time, but only one of them has time and concentration. So if we're looking for time and we have concentration, we're going to use our integrated rate law. So we're going to plug in. So we're interested in the time when the concentration is 5 times 10 to the negative 4th. So we're going to do the natural log of 5 times 10 to the negative 4th. That equals negative K. We determine our K to be 6.08 times 10 to the negative 4th times T plus the natural log 6.94 times 10 to the negative second. So we would take our equation and we would rearrange to solve for time. And we would end up with a time of 8,110 seconds. So we've just determined how long it takes to get a particular change in our concentration using our integrated rate law. Now with F, we want to know the concentration at 1,455 seconds. So we're using the same initial information, same K. We're just looking at a different time. This time we want concentration and we have time. We're still relating concentration and time, so we're still using our integrated rate law. This time we want the concentration at time t. So we're going to plug in our K. We're going to plug in our time. And we're going to plug in our initial concentration. Now, performing the calculation on the right side of that equation, I'm going to get that the natural log of my concentration equals negative 3.553. We're not done solving this problem. We're not looking for the natural log of the concentration. We want the concentration itself. So again, we've got to go back and use some log rules and some exponential rules. And so we're going to use the rule that e to the natural log of x equals x. So we're going to do e to both sides. So e to the natural log of the concentration equals my concentration. E to the negative 3.553 will equal 2.87 times 10 to the negative second molar. So we've just looked at examples where we can either determine how long it takes to get a concentration change, or we can determine the concentration after a certain period of time. Our final question is asking us the concentration after 7 half-lives have passed. So when we talked about half-life, we saw the equation that the concentration at any time is the concentration at time 0 divided by 2 to the n. So the concentration at time 0 is my initial concentration of 6.94 times 10 to the negative second molar divided by 2 to the n, where n is the number of half-lives that have passed. So this would be 2 to the 7, which is going to give me a concentration of 5.42 times 10 to the negative fourth molar.